Hey chemists, here is a promise video. I'm going to review London dispersion forces, trends in boiling point, dipole-dipole interactions, and cover hydrogen bonding. So we've been talking about intermolecular forces, and we started with London dispersion forces, and you'll see over here these pink and blue boxes, pink and gray boxes are just to keep your eye focused on what I am talking about so you don't get distracted with everything else that is happening on this video. So if you'll focus your attention, this graph should look familiar, and we've discussed quite a bit that LDFs, or London dispersion forces, because that's way too long of 3 words to write out, are temporary or instantaneous dipoles that occur in nonpolar molecules. And we talked about LDFs being a temporary dipole that arises when the electrons in the atom is lopsided, so that within the atom there is for an instant, a negative side of an atom and a positive side of an atom, which then induces a negative side and a positive side in the adjacent atom, and it is a cascading effect. And these instantaneous dipoles are what leads to the London dispersion forces. They are the weakest of the intermolecular forces, and they are temporary. That means they come and go and come and go. We were also comparing, as you see in the graph here, boiling point versus relative molecular mass. And there are 2 separate lines for a reason, which I will explain in the next graph below. Here we have halogens, here we have noble gases, and we see that if we compare only noble gases, we see that an increase in the molecular mass of the fluorine, chlorine, bromine, iodine molecules leads to an increase in boiling point. And the justification for this trend is the following. If the molecular mass increases, that means there are simply more electrons around to undergo instantaneous London dispersion forces. And if you have more electrons with more London dispersion forces, you have just overall more London dispersion forces occurring, and therefore it's going to take a greater amount of energy to change state, boiling point meaning we're going from a liquid to a solid. So if I pull down this, so then giving you another visual, as the MR increases, the molecular mass increases, LDFs increase due to increased number of electrons. More electrons means more chances for instantaneous dipoles to form. From the first graph here, there's a clear correlation between molecular mass or atomic mass, as in the case of the helium, neon, argon, krypton, and xenon, and the boiling point. And then I remind you here that a change of state involves only intermolecular forces, not the intramolecular forces, which occur between the halogens. And these intermolecular forces must be broken. I put broken in parentheses because even in the gas phase, the gas state, there are very, very loose intermolecular forces. And therefore, we're really talking about LDFs being relaxed. And the more London dispersion forces you have, the more energy that is going to be required for that phase change or change of state from liquid to solid. And thus we see a higher boiling point with respect to molecular mass. If we look and compare hydrocarbons, which comes in topic 10 when we talk about organic chemistry. And notice that there is not so much a linear trend, but more of a kind of exponential reverse trend where we have once again a clear trend between molecular mass and boiling point. Hydrocarbons consist of only carbon and hydrogen atoms, and they're all nonpolar. So we are comparing a specific type of molecule with respect to its molecular mass and what is the trend with respect to boiling points. And we see there is a clear correlation. Why is this so? Well, we might be able to predict, before I undo my gray box with a pink border, greater molecular mass. It also, as a halogen's molecular mass increases, its length, the carbon chain also increases. But we really are increasing the number of electrons. And the number of electrons lead to it. The greater the number of electrons, the greater the intermolecular forces, and therefore we see this trend, which is exactly, I'm going to just take that away for you. So as length and molecular mass increase for halogens, we once again see a trend for molecular mass and boiling point. Again, London dispersion forces arise through the lopsidedness, instantaneous dipoles that arise in weak intramolecular forces. However, nonetheless, the greater the number of London dispersion forces, the greater the energy required to change state. Again, boiling point, of course, meaning that we are moving from the liquid state to the gas state. I posted this slide in a lesson last week, and I couldn't explain this. It's like, okay, chlorine has a lower molecular mass, but a higher boiling point. So that sort of flies in the face of what we've just been discussing. As the book states, you have to be very careful about when you compare molecules and try to look at their trends. We are comparing two groups of elements / molecules. We are looking at the trend for both halogens and noble gases, and we see that the trend doesn't hold. So you have to be really careful as a chemist to make sure that you're looking at all things being as equal as you can, looking at all halogens, looking at only noble gases, comparing elements or molecules of similar molecular mass, which we will do in the next video. So this graph is a little less clear than the above two for the pure and simple reason that we are comparing two different types of elements, and therefore we might expect that a trend that we're looking for does not get supported as we see in the above, and then I have that for you. Yes, this graph shows that a trend for boiling point does not exist. Chlorine is higher than krypton, and therefore we have to be really careful when we do those comparisons. So that's an overview of London dispersion forces. I'm going to stop there so that the video doesn't get too long and it's easier to upload to wherever I need to upload it so you can have a look. All right, chemists, I hope that was helpful. Bye for now. And getting out of here. Here we go.